In this video, we introduce our method to RGBD-SLAM, which we call Loopy-SLAM. Recently, dense neural SLAM like point SLAM has been introduced, achieving impressive rendering quality and pose estimation. However, point SLAM still struggles in real-world conditions with its frame-to-model tracking paradigm, which lacks global consistency. This leads to significant camera pose drift and corrupted maps as a result. On the other hand, GoSLAM is an RGBD SLAM system with global consistency, but suffers from poor rendering quality due to its application of loop closure and global BA on a hash grid representation, which cannot easily be deformed, but instead requires remapping strategies in the form of retraining the features stored in the grid. Due to the reoccurring global updates of poses in GoSLAM, the map optimization therefore does not settle and shows difficulty in converging. With Loopy-SLAM, we show that it's possible to achieve global map consistency while maintaining high-quality renderings of the scene. We do this by using a neural point cloud similar to point SLAM. With explicit points compared to, for instance, grids, map deformations are straightforward. This means that remapping strategies are not needed. By using submaps, we show that we need not store all mapped frames, as is the case with methods employing remapping. Our method works by collecting a video sequence from an RGBD camera. We represent our 3D scene with a neural point cloud where each point has optimizable features. We use a re-rendering loss to the sensor input to optimize the map and the camera pose. Submaps are progressively created as the scene is explored, and the pose is optimized locally against the last added submap, the so-called active submap. Every frame, we check if a new keyframe should be created. If not, we map against the active submap and query the next frame from the video. If yes, we initialize a new submap and map it. Next, we add the new global keyframe to our bag of words database before we query the next frame from the video stream. We also check if a loop is detected every time a new submap is created. If a loop is found, we perform global pose optimization as follows. First, we compute the constraints, meaning the relative pose between the loop edges. This is done via point cloud registration of the submaps, here denoted S1 and S4. Next, we collect all constraints and construct a pose graph which we solve to retrieve the corrected global keyframe poses. Given the global keyframe poses, we then correct the corresponding submaps rigidly. Finally, we proceed with tracking the new submap. Now we show how our system works in practice. Here we see the first submap and associated camera pose in red. As the scene is explored, we overlay the individual submaps. At one point, the camera pose drift has grown large, as can be seen by the distorted hallway and corner of the room where the submaps do not align well. At this point, a loop is found in the hallway, and the pose graph optimization corrects the drifted geometry and trajectory. Finally, as the whole scene has been explored and all data is fused into a global map, no visible seams are left. We find that our method achieves greater reconstruction accuracy than existing methods and comparable tracking performance to GoSLAM. Here we show the mesh on one of the TUM dataset scenes. In terms of rendering accuracy, we are similar to point SLAM. Here we show some random frame renderings on the replica dataset. We presented Loopy-SLAM, which enables loop closures for dense SLAM using a deformable neural point cloud. Our approach does not require remapping of scene parts which are affected by loop closures due to the direct deformation of the underlying scene representation. We also do not need to store all mapped frames, which previous methods required for remapping the scene during loop closure.